the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is actually a second video in a series on the Gram-Schmidt process. You usually learn about this topic as a subtopic within the Gram-Schmidt process. It's called QR factorization. It's basically how to factor a given matrix into the product of two matrices, one of which has columns that form an orthonormal basis for the column space of the given matrix, and the other matrix is an upper triangular invertible matrix with positive entries along the diagonal. And that's exactly what this theorem states. If A is an m by n matrix with linearly independent columns, that's very important, then A can be factored as A equals QR, where Q is also the same size matrix as A. However, Q has orthonormal columns and they form an orthonormal basis for the column space of A. R, on the other hand, is a square upper triangular invertible matrix with positive entries on its diagonal. Rather than proving this, I'm just going to use it. And the big question is, how in the world do you actually do the factorization? It seems like it should be very, very difficult. Well, this all hinges upon one thing we know from the past. We had a theorem a while ago that if we have an orthogonal matrix, in this case we'll call it Q because that's what our matrix is going to be. Remember, if a matrix has orthonormal columns, we would call it an orthogonal matrix, unfortunately. Well, if that's true, then Q transpose times Q should be the identity matrix. And that's again from a previous theorem. It'd be theorem 6 in the book that I use. I have no idea what theorem it is in the book that you use. However, that means if you take Q transpose and multiply it by A, and if we can factor A into Q times R, then that's Q transpose times Q times R. And that's actually what I have on the second line right here. Of course, Q transpose times Q, since Q is an orthogonal matrix or a matrix with orthonormal columns, well, that product is the identity matrix, and the identity matrix times R is just going to be R itself. And that's how we get R. The question is, how the heck do you get Q? How do you get an orthogonal matrix given that matrix A? That is, you have some matrix, the matrix you're given, all of its columns are linearly independent, and somehow you're supposed to create a matrix from that matrix A where the columns of your brand new matrix are all orthogonal to one another. Not only that, but they're orthonormal. Well, if you've just finished watching my video on the Gram-Schmidt process, well, guess what we're going to do? The Gram-Schmidt process. Because the reality is we have n linearly independent columns, so we have n linearly independent vectors. And what we can do is the Gram-Schmidt process to create n brand new vectors that are orthogonal to one another. Then we can normalize them so that they are orthonormal, and we can place those in the matrix Q. Once we have the matrix Q, we can find R by using this right here, Q transpose times A. Just take Q transpose, multiply it by the original matrix A, you will actually have R. And therefore you have your matrix factorization Q and R. And that process is stated here. Given an m by n matrix, factor it into the product Q times R, where Q is m by n with orthonormal columns forming the basis for the column space of A, and R is an upper triangular matrix with positive entries along its diagonal. By the way, it's also invertible. So we use the Gram-Schmidt process along with normalization to construct the matrix Q from the columns of A, and then R is Q transpose times A. Now, this process usually helps for matrix computations when it comes to computer algorithms. So this is kind of important to know. It's also kind of a pain to do by hand, but we're going to go ahead and showcase it here. So let's go ahead and use this process to find the QR factorization of this given matrix right here. Well, the first thing we need to do is probably label the columns appropriately. So I'm going to call this column U sub 1 and U sub 2 and U sub 3. And then we'll use the Gram-Schmidt process to create orthogonal vectors related to these vectors. So we're going to choose one of those vectors. It is very common to always choose the very first vector. So I'm going to let v sub 1 equal that first vector u sub 1, and that'll be 1, 1, 0. Now, one thing I want to mention that I didn't really mention in the last video, once you have a computation done like this, so you have your vector v sub 1, and you're going to move on to find the vector v sub 2 and so on and so forth, you'll need to find eventually v sub 1 dotted with v sub 1. You might as well just list that out. Off to the right is a good idea. So I'm going to go ahead and say that right here. V sub 1 dotted with v sub 1, mainly because that's never going to change. Throughout this entire process, you're going to need to constantly reference what is v1 dotted with itself. Well, that's just 1 plus 1 plus 0 or 2. Now we'll go ahead and create v sub 2. And that's sort of like u sub 2. However, we're going to remove the orthogonal projection of u sub 2 onto the vector space spanned by v sub 1. So there we go. Let's go ahead and steal all that information. U sub 2 is 2, 1, 3. U sub 2 dotted with v sub 1. That's going to be this vector dotted with this vector. That's 2 plus 1 plus 0, or in other words, 3. And then we're going to divide that by v sub 1 dotted with itself, which we wrote over to the side, it's 2. And we're going to multiply that by v sub 1. And we get down to this guy right here. Again, like I mentioned before, once you get to a vector like this, v sub 2, go ahead and find v sub 2 dotted with itself, because you're going to use it in the next step. You might as well just compute it while you're here. That's going to be 1/4 plus another 4th plus 9. And that's going to be 19 halves. Now we move on to the next step. Another thing I want to mention is that even though we want to end with orthonormal columns for Q, the process of normalizing the columns can be held off until the very end. If you choose to normalize right now, it's going to be an absolute mess. So always normalize at the very end. Well, v sub 3 is, again, just like u sub 3, except we're going to remove the projection of u sub 3, or what I commonly call the shadow of u sub 3, onto the subspace spanned by the vector v sub 1. So we're removing that shadow. We're also going to remove the shadow of u sub 3 onto the vector space spanned by v sub 2. Doing so will create a vector orthogonal to both v sub 1 and v sub 2. So let's go ahead and write all that down. U sub 3 is 1, 1, 1. U sub 3 dotted with v sub 1 is going to be 1 plus 1, or in other words, 2, divided by v sub 1 dotted with itself. But luckily we wrote that down over to the right. That's a 2. And multiply that by v sub 1, which is 1, 1, 0. Now we'll take u sub 3 and dot it with v sub 2. That's going to be 1/2 minus 1/2 plus 3, so that's 3, divided by v sub 2 dotted with itself, which is 19 halves. And finally, multiplying by v sub 2. And now we just have some arithmetic, which honestly can be an annoyance at times. All right, we're done with the Gram-Schmidt process. You can double check these vectors are actually orthogonal to each other. v1 dotted with v2, it's 1/2 minus 1/2 plus 0. That's definitely 0. So v1 and v2 are orthogonal. v1 dotted with v3, well, that's going to be a negative 3/19 plus 3/19 plus 0. So those two are orthogonal. And finally, v sub 2 dotted with v sub 3, that's going to be a negative 3/38 minus another 3/38. That's a negative 6/38 plus 3/19, which is plus 6/38. So that's all 0 right there as well. So we definitely have orthogonal vectors now. Now we just need to normalize them. And the norms of these vectors, actually, maybe I should say, you should find v sub 3 dotted with itself, because the norm of the vector v sub 3 is the square root of that result. So v sub 3 dotted with itself is 9/19 squared plus another 9/19 squared. So that's 18/19 squared, plus 1/19 squared. So that's going to be 19/19 squared, which is 1/19. Now remember, the norm of each of those vectors, v1, v2, and v3, are the square roots of those numbers right there. So it is actually not too bad if you take the dot product of a vector with itself to find the norm. It's just a square root of that result. So let's go ahead and write that down. I'm actually going to create new vectors here. I'm not going to use v1, v2, and v3. Instead, I'm going to call them the normalized version of v1, the normalized version of v2, and the normalized version of v3, using a notation I've used in the past. That is that notation right there. That's going to be the normalized version of v1. Remember, we're going to take v1 and divide it by the square root of that number. So that is the normalized vector version of v sub 1. Now let's find the normalized vector version of v sub 2. Remember, we're going to divide by the square root of that number, or in other words, multiply by the reciprocal of the square root of that number. That's another way of thinking about it. Notice I went ahead and I didn't actually rationalize the denominator. I just multiplied both numerator and denominator of that last entry by the square root of 2 so that these all have the same denominators. No real reason for that, just it looks better to my eyes. And finally, down here, the normalized version of v sub 3 is this guy right here. Those vectors, the normalized versions of v1, v2, and v3, are going to form the columns of Q. Now, some fair warning to you. Orthogonal matrices often look like an absolute mess. There's no way around that. That's just how it is. Now our job is to find what R is. I happen to know that A is going to be Q times R. And because Q is an orthogonal matrix, I know that Q transpose times Q is the identity matrix. So therefore Q transpose times A, where A is Q times R, is going to be the identity matrix times R. So therefore to find R, we just compute what Q transpose times A is. It's not a fun process, but let's just go ahead and do it. Q transpose, let's write that one down first. And we're going to multiply that by A. In fact, let me go ahead and scoot that over because I don't want to rewrite that whole silly matrix. So A, I'll copy down. And now we do matrix multiplication, which looks to be a pain here. Let's go ahead and suffer our way through it. Now, the interesting thing about that multiplication is that it will always be an upper triangular matrix and it will always have positive entries along the main diagonal. So really you don't actually have to compute these pieces right here because you know they're going to be 0. Also, I kind of joked around a little bit that the computations were going to be pretty hard, but they're not. They're actually pretty easy because you're adding things with like denominators, so it's not too bad. But there you go. That's the QR factorization. That right there is the matrix R. Now we will learn why we use QR factorization methods a little bit later, but what's important is that you get practice using the QR factorization method. It gives you practice with the Gram-Schmidt process, but then on top of that, it allows you to see where you're going in the future, not to know why you're doing it, but where we're going eventually. All right, I'm done with this video. I hope it helped out, and I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.